In this video, I'm going to show you the crossed Aldol condensation. Let's jump right in. In a previous video, I showed you the Aldol condensation. You can click on the link and go back and review that if it's helpful. But in this video, I'm going to show you the crossed Aldol condensation. Cross just means we use two different types of molecules instead of the same molecule as both parts of the aldol condensation. So let me give you an example. I can have a compound like, let's put a phenyl over here. So this carbonyl compound has hydrogens on this alpha carbon, but there are no hydrogens on this alpha carbon. So if I use a base to make an enolate, I can pull off one of those protons. So my carbonyl has a CH2 with a negative carbon on that side, and on this side we'll just write phenyl instead of drawing it out every time. Now if I want to use a different molecule, we might have some more of those in there, right? There's quite a few of those in my compound. But if I want to make sure it reacts with a different molecule, maybe I use something like this. I'm going to put a phenyl carbonyl hydrogen, benzaldehyde. On this carbonyl, there are no alpha carbons here, and this alpha carbon has no hydrogens on it. So there are no spots where this base would pull off a hydrogen from an alpha carbon. So this would be made, but nothing happens to this benzaldehyde. Now I'm going to draw that phenyl carbonyl hydrogen. Phenyl carbonyl hydrogen. Phenyl carbonyl hydrogen. Phenyl carbonyl hydrogen. So in this reaction, let's say I run the reaction with very little acetophenone and a whole bunch of benzaldehyde. Once one of these molecules hits the hydroxide and is deprotonated, and it's on the hunt to go react with a carbonyl, what are the odds it finds this carbonyl of another acetophenone versus a benzaldehyde? You're right, of course, it's more likely to hit a benzaldehyde if I run with a whole bunch of those. So I hit that one, electrons go up onto the oxygen. Do they come back down? Phenyl's a bad leaving group, hydrogen's a bad leaving group. So no, they stay up there. So here's what we make. We make a phenyl carbon with an O-. There's a hydrogen on here. And this carbon is now attached to this CH2, attached to this carbonyl, attached to this phenyl. It stays like that until I protonate with acid and water. So I have phenyl, COH, H, CH2, carbonyl, and phenyl. If it dehydrates, losing my H and my OH, I make phenyl, carbon, hydrogen, double bonded now to this carbon with a hydrogen, to this carbonyl, to this phenyl. If I take my final product, I can cover up one side of the double bond to make sure I start with my starting material. There's the benzaldehyde. And I can cover up the other side of the double bond with my two hydrogens, and there's my starting material, phenyl, carbonyl, methyl. So I have both pieces of my starting material, both reactants, in my final product. So this is my correct product, a crossed aldol condensation. So here are the two things you need to consider whenever you do a crossed aldol condensation. One, whenever you have two molecules in there, it's best if only one of those two molecules can be deprotonated at the alpha carbon. So for example, if I have a carbonyl, if there's a hydrogen at the alpha carbon, it can be deprotonated. But what types of things can I have over here that would not be deprotonated? Well, you could have a hydrogen like aldehyde. There's no alpha carbon there. You could have a phenyl ring is common because there's no hydrogen on that alpha carbon. You could have a terbutyl group because there's no hydrogen on this alpha carbon, only on the beta carbons. So no hydrogen here, no hydrogen here, no alpha carbon here, only this one would be deprotonated if these two molecules were in there. So if I add my base, it would pull off this proton, but nowhere else. So I'd make this. This is perfect for a crossed aldol. Now I have this other compound in there. Now which one of these do I want to have extra of? Well, if I wanted to make sure this hits the other molecule and not one of itself, I need to run with an excess of this compound. A whole bunch of the one I want to be attacked. So then it would come and attack. Electrons would go up. And I'd end up with O-, terbutyl, phenyl. This carbon has CH2 to my carbonyl O and H. I protonate with acid and water. I dehydrate with my water, and I get a double bond. There's a terbutyl and a phenyl on the left side, a carbon with a hydrogen, and my carbonyl hydrogen. I can cover it up to make sure I've got my starting materials. There's my starting material aldehyde, and there is my terbutyl phenyl ketone. So I've got my two pieces. This is my product. So let's just see how we can quickly jump to the final answers. So what if we were given something like, here's that same problem, but instead of going through the entire mechanism, let's just try to jump to the final answer. So we know that this is the one that has alpha carbon hydrogens that will be deprotonated. There are none here, and none here. So this is the one where I'm going to lose a hydrogen. This is the one where I'll lose the oxygen then. So let's start by drawing this one where I'm going to lose the oxygen. So I draw this without the oxygen, and since I know this is the one where the hydrogens will be removed, I'll take off two of those hydrogens, so I'll draw the carbon. Only one hydrogen remains, and then I just draw the rest of it. So once you know which one the hydrogens are going to be removed from, which one the oxygen will be removed from, you can draw your double bond. Then you can double check to make sure that, yep, I've got that, and yes, I've got that. That's how you can quickly draw it. Hey, I hope that helps. Think about subscribing to the channel so I can help you more with your organic chemistry.